Good evening, everyone. My name is Nidhi Kaushik. I will be your TA for this course, Differential Equations for Engineers. So, you all must have attended the class on the Google Meet, but due to some issues, I could not record the class. So, I am taking this again, so just for the purpose of recording. So, I hope you all must have watched or gone through the lecture videos and are familiar with the basic concepts required to solve the differential equations. Uh, so we'll and Shortly you must have got the assignment as well. We'll be doing some questions which are similar to those in the assignment, not the exactly same one, so that you get the idea how to solve them. So let's start. I hope my screen is visible now. So today we'll be starting with tutorial 1. So the first question is solve y under root 1 plus x square dy plus x under root 1 plus y square dx equals to 0. So one can see that very easily we can make take all the terms involving the variable y and the variable x on either side of the expression. So let me write it. So taking the terms involving variable y on one side and the terms involving variable x on the other side, we get the following. So now we can easily integrate both the sides. Integrating both sides, what we get? Integral y under root 1 plus y square dy equals to integral x upon under root 1 plus x square dx. Now we'll try to solve these integrals. We can see that the denominator has terms of this form 1 plus y square. So if we get something like its derivative on the numerator, then we can use the substitution method. For that, we'll just multiply and divide the term by 2. Similarly here also, to 1 by 2. Now we'll do substitution. Let u equals to 1 plus y square. This gives us du equals to 2y dy, and 1 plus x square is equal to some other variable v, which gives us 2x dx is equal to dv. So now our expression is 1 by 2 integral du upon under root u is equal to 1 by 2 integral dv upon under root v. Now using basic integral of some power of u, we get 1 by 2 u to the power 1 by 2 1 2, which is equal to 1 by 2 2 root v plus some constant c. So this gives us under root u is equal to under root v plus some constant c. Now replacing the value of u and v as we had taken the substitution, we get, again, It should have been a minus over here. Minus, 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 minus. So this gives us under root 1 plus y square plus under root 1 plus x square is equal to c. This is the solution. So I hope this is fine. If you have any doubt regarding any step, please let me know. You can just tell me in the chat option of the classroom. So our next question is solve dy by dx equals to minus under root 1 minus x square upon 1 minus y square. Again, clearly we can separate the terms involving variable x and variable y on either side of the equation. So writing the problem again in a good way, we get under root 1 minus y square dy is equal to under root 1 minus x square dx. Now we can easily integrate it. Integrating both sides, we get integral under root 1 minus y square dy minus is equal to minus integral under root 1 minus x square dx. So you all must have studied in your school time that this integral under root 1 minus x square dx is given by y by 2, sorry, x by 2 under root 1 minus x square plus 1 by 2 sin inverse x by a. We actually had this under root a square minus x square. We have the formula for this as x by 2 under root a square minus x square plus a by 2 sin inverse x by a. So using this formula, we get y by 2 under root 1 minus y square plus 1 by 2 sin inverse y is equal to minus x by 2 under root 1 minus x square plus 1 by 2 sin inverse x plus some constant c. So writing it, simplifying it, we get y root 1 minus y square plus x root 1 minus x square plus sin inverse y plus sin inverse x is equal to some constant c1, where basically c1 is equal to 2 times c. So this gives us the solution. I hope this is fine. I don't think we have done anything new in this problem. So let's move to the next question. Question third. Solve x cube plus 3xy square dx plus y cube plus 3x square y dy is equal to 0. Here we can see that all the terms have degree, total degree. That means the power of x and plus the power of y is 3 everywhere. When we have such a case, we can use the method of solving an homogeneous equation. Basically, in this case, we can convert our problem into the problem of homogeneous equation. So let's see how we will do that. Solution. So we have x cube plus 3xy square dx is equal to minus y cube plus 3x square y dy, which gives us dy by dx is equal to minus x cube plus 3xy square upon y cube plus 3x square y. Now, if we divide the numerator and the denominator by x cube, we get this is equal to minus x by y cube plus 3y by x square. Sorry, we are dividing it by x cube. So we get 1 plus 3y by x square upon y by x cube plus 3y by x. So now we have the homogeneous equation. So how do we solve such an equation? We start with the substitution. We take some other variable t to be equal to y by x. This gives us dt by dx. Sorry. This gives us dy by dx is equal to t plus x dt by dx. Now putting the value of dy by dx from here to here, we get t plus x dt by dx is equal to minus 1 plus 3t square upon t cube plus 3t. So this gives us x dt by dx is equal to minus 1 minus 3t square minus t power 4 minus 3t square upon t cube plus 3t, which is, taking minus common, 1 plus 6t square plus t power 4 upon t cube plus 3t, which implies taking the terms involved. Now this is something of the type separation of variable. Taking all the terms involving variable t on one side and the terms involving variable x on the other side, we can easily integrate it and hence find the solution. So we get t cube plus 3t upon t power 4 plus 6t square plus 1 dt is equal to minus dx by x. So now integrating both sides, we get integral t cube plus 3t upon t power 4 plus 6t square plus 1 dt is equal to minus integral dx upon x. Now here in the denominator we have x, in the numerator we have 1, so easily its integral is 1 log x. And on the left hand side we can see that the denominator is t power 4 plus 6t square plus 1, and its derivative would be something 4t power cube plus 12t. So in order to get the numerator something of the form of the derivative of the denominator, we would just multiply and divide it by 4. Now we'll do the substitution. We'll let v to be equal to t power 4 plus 6t square plus 1. That gives us dv is equal to 4t cube plus 12t square times dt, which is basically the numerator. So this gives us 1 by 4 dv upon v is equal to minus integral dx upon x. Now integrating, we get 1 by 4 ln mod v is equal to minus ln log x, sorry, ln mod x plus some constant, will take it to be ln c, so that we can use the properties of logarithm. This gives us v is equal to c by x to the power 4, because some constant times log x is equal to log constant to the power x to the power constant, and log x plus log y is equal to log x y. Basically, using these two properties, one can easily reduce this. So we get v is equal to some other constant c1 upon x power 4. Now replacing the value of v, what was v? V was t power 4 plus 6t square plus 1. This gives us t power 4 plus 6t square power 4 plus 6t square plus 1 is equal to c1 by x power 4. Now what was the value of t? T was y by x. Replacing the value of t in the final solution, we get y by x to the power 4 plus 6y by x square plus 1 is equal to c1x to the power 4. Now taking the LCM on the left hand side as x power 4, we get y power 4 plus 6 x square y square plus x power 4 upon x power 4 is equal to c1 by x power 4. So cancelling out these two terms, we get y power 4 plus x power 4 plus 6x square y square is equal to constant c1. So this is the solution. So I hope the solution was fine. If there is some doubt in any step, please let me know. Next, now let's move to the next question. Sorry. Solve dy by dx is equal to y by x plus cos y by x. Since already we have the problem in the variable y by x, it is clear that this is a homogeneous equation. So we'll start with the standard method used to solve the homogeneous equation, which is to through substitution. We take some other variable t to be y by x and then play with dt by dx instead of dy by dx, and at the end when we have the solution in terms of t, we'll replace the value of t. So solution, we have, let t to be equal to y by x. This gives us dy by dx is equal to t plus x dt by dx. Now putting the value of dy by dx in terms of t, we get t plus x dt by dx is equal to t plus cos t. Now this t gets cancelled out. We are left with x dt by dx is equal to cos t. Now we can see that we can easily uh, separate the terms involving variable t and variable x on either side. So we get dt by cos t is equal to dx by x. Now integrating both the sides, we get integral dt upon cos t is equal to integral dx upon x. Now we know that 1 upon cos t is actually secant t, and we also know that the integral of secant x is given as ln secant x plus tangent x. So, and 1 upon cos x is equal to secant x. Now using this information, we get ln secant t plus tangent t is equal to ln x, because integral of 1 by x is ln x, plus some constant, we'll take it to be ln c, so that we can use the properties of logarithmic function. So this gives us secant t plus tangent t is equal to some constant times x. Now since secant t is 1 by cos t, 1 by cos t, and tangent t is sin t by cos t, we get 1 plus sin t upon cos t is equal to some constant c times x. Now replacing the value of t, what was t? T was y by x. We get 1 plus sin y by x is equal to cx cos y by x. this gives us the solution. All these solutions that we are finding are actually the general solution, because we have this constant, arbitrary constant c in our solution. So by solution we mean the general solution. Okay, I hope this solution was fine with everyone. Please let me know if you have any doubt. Let's move to the next question. Solve x plus 2y minus 1 dx plus x plus 2y plus 1 dy is equal to 0. Solution. So let's start with looking how dy by dx looks like. So we have x plus 2y plus 1 dy is equal to minus x plus 2y minus 1 dx. This gives us dy by dx is equal to minus x plus 2y plus 1 upon x plus 2y plus. Here we can see that we have everything is in the form of x plus 2y. So we can take some new variable x b or some variable t to be x plus 2y. So our problem would be something linear upon linear in terms of this new variable. So let's take the substitution. T equal to x plus 2. This gives us dt by dx is equal to 1 plus 2 times dy by dx. Now this dy by dx in terms of t is minus t plus 1 upon t plus 1. We have just replaced x plus 2y by t from here and put it here. So this gives us just equal to t plus 1 minus 2t minus 2 upon t plus 1. Just basic taking LCM and solving the fraction. We get minus sorry, this is plus 2. We get minus t plus 3 upon t plus 1. So again we are now in the framework of separation of variable. Separating the terms involving t variable and x variable, we get t plus 1 upon 3 minus t dt is equal to dx. Now integrating both sides, we get integral t plus 1 upon 3 minus t dt is equal to integral dx. Now to solve this left hand side, we can see that the numerator and denominator are some linear functions in t. So the idea to solve such an integral is to make terms in the numerator and denominators same so that the terms cancels out. So with that thing in our mind, we will write this integral as minus 3 minus t. So this is basically minus 3 plus t. We want plus 1, so we will add a 4 on 3 minus t dt, and integral of 1 is x plus some constant c. Now separating the terms, we get integral dt minus plus 4 times dt upon 3 minus t. 1 upon linear, we know we can easily integrate it. This constant. This gives us minus t plus 4 ln 3 minus t upon minus 1 is equal to x plus c. This gives us, now we can replace the value of t. What was t? T was x plus 2y. Putting the value of t, x plus 2y in the final solution, we get minus x minus 2y minus 4 ln 3 minus x plus 2y is equal to x plus c. Taking this x on the left hand side, we get minus 2x plus 2y plus 4 ln 3 minus x plus 2y is equal to c. Taking c1 to be equal to minus c, we get 2x plus 2y, or in fact minus c by 2. We can also take 2 to be common. We get x plus y plus 2 times ln 3 minus x plus 2y is equal to c1. So this is the final solution. And it is quite interesting that this problem can be solved in another way as well. So what was the problem? The problem was x plus 2y minus 1 dx plus x plus 2y plus 1 dy equals to 0. Now if we take this to be some function m of x and y, this to be some function n of x and y, we have del m by del y is equal to 2, and del n by del x, oh, this is not exact. So no, we cannot use the method of exact equations. Okay. So let's not think about that. We'll solve some problems of exact equation further. So this problem was mainly solved by taking the substitution. The main important substitution was this one. So I hope it was clear. So let's move to the next question. Question 6. Solve dy by dx equal to x plus 2y x plus 2y minus 3 by 2x plus 3, 2x plus y minus 3. Now here we can see that we cannot easily separate the variables, and substitution would also not work. So and the degree the degree of the terms, this is 1, but here the degree is 0. So we'll try to convert this differential equation in a form so that this term with 0 degree becomes 0. We'll do some substitution in such a way, we'll take the substitution in such a way that the terms that involve x power 0 and y power 0 turns out to be 0. So let's see how we'll do that. Solution. Let capital X to be x plus some h. This gives us dx is equal to dx, and capital Y equals to y plus some variable k, some constant k. Dy, where this gives us that dy is equal to dy. Now the main important part, the main factor that will make our problem easier is the value of these h and k. We'll tactically take the values of h and k so that our problem becomes of the homogeneous type. So let's see how we'll do that. Now, putting the value of small, no, no, okay, there was a slight mistake. We'll take small x to be capital X plus h, small y to be capital Y plus k. Now replacing the value of x and y, we get dy by dx is equal to x plus 2y plus some constant. That constant would be h plus 2k minus 3 upon 2x plus y plus some constants. That would be 2h plus k minus 3. Now we want these terms to be 0. That means we want h plus 2k minus 3 is equal to 0 is equal to 2h plus k minus 3, or we want h plus 2k to be equal to 3 and 2h plus k is equal to minus 3, plus 3. Then the constant terms will be 0 and our problem would be left, we would be left with only this much part, which can be made homogeneous. So we'll use the basic elimination method to solve these equations. So multiplying the first one by 2, we get 2h plus 4k is equal to 6. 2h plus 2k is equal to 6 minus minus minus. This gets cancelled out. We are left with 2k . think I did some mistake. Yes. I'm so sorry. Here we don't need any kind of multiplication. We are not multiplying anything. So this is 3k is equal to 3, which gives us k is equal to 1. Now putting the value of k here, we get h is equal to 3 minus 1 upon 2, which is again 1. So therefore, we have k is equal to 1, h is equal to 1. Thus, we have small x is equal to capital X plus 1 and small y equals to capital Y plus 1. And dy by dx is equal to x plus 2y upon 2x plus y. Now dividing the numerator and denominator by capital X, we get 1 plus 2 times y by x upon 2 plus y by x. Now the problem is of the form homogeneous. So we'll again use the standard methods to solve a homogeneous equation, which is to start with the substitution. We substitute y by x by some other variable t. Let t to be equal to y by x. This gives us dy by dx equal to t plus x dt by dx. Now using the value of dy by dx from here in the terms of t and putting it here, we get t plus x dt by dx is equal to 1 plus 2t upon 2 plus t. This implies x dt by dx is equal to 1 plus 2t minus 2t minus t square by 2 plus t, which is 1 minus t square by 2 plus t. Again, we are in the framework of separation of variable. So we'll separate the terms involving variable x and the variable t on the either side. We get 2 plus t upon 1 minus t square dt is equal to dx by x. Now integrating both sides, we get integration 2 plus t upon 1 minus t 1 plus t dt is equal to integration dx by x. Now this can be written as 1 minus t minus plus t upon 1 minus t 1 plus t dt is equal to dx by x. One can see that why we did such manipulation, so that we can separate these terms, and in one of the case we can the term 1 minus t gets cancelled out. So separating it, we get minus integral 1 upon 1 plus t plus 3 times integral dt upon 1 minus t 1 plus t is equal to integral dx by x. This gives us minus 1 upon 1 plus t plus 3 integral 1 upon 1 minus t plus 1 upon 1 plus t. This would give us a 2 in the numerator. So we'll divide it by 2, which is equal to integration dx by x. So 3 by 2 minus 1 would be 1 by 2. We are left with 1 by 2 dt upon 1 plus t plus 3 by 2 integral dt upon 1 minus t is equal to integration dx by x. Now integrating both the sides, we'll get 1 by 2 ln 1 plus t plus 3 by 2 ln 1 minus t is equal to ln x plus ln c. We took the constant to be ln c again, so that we can use the properties of logarithmic function. This gives us ln 1 plus t 1 minus t cube is equal to 2 times ln xc, which is 1 plus t 1 minus t cube is equal to some constant c1 x square, where c1 is c square. Now replacing the value of t, we get I think there is some issue. Yes, here we will have minus 1. So the integral would be, this would be ln 1 plus t upon 1 minus t cube, because we have a minus, which gives us 1 plus t by 1 minus t cube. Now putting the value of t, what was t? T was pi by x. 1 plus y by x upon 1 minus y by x cube is equal to c1x square. This implies x plus y upon x times, let's not cross, times x cube upon x minus y cube is equal to c1x square. Now this gets cancelled out. We are left with x square, and this x square gets cancelled out by this x. So we are left with x plus y is equal to c1 times x minus y cube. Now what was the value of capital X and capital Y? Capital X is small x minus 1 and capital Y is small y minus 1. And these values in the final solution, we get x plus y minus 2 is equal to C1 x minus y cube. So I hope this solution was fine with everyone. If you have any doubt, please let me know. So here we had mainly used the method used to solve a homogeneous equation, and to convert our problem into a homogeneous equation, we have done some tactic substitution. We have taken h and k according to us. Being constant, we have the liability because its derivative would turn out to be 0, so dy by dx won't change. Okay, so let's move to the next question. Question number 7. Solve x cubed y cubed plus 2xy dy is equal to dx. Solution. Firstly, let us see how does our dx by dy looks like. This time we'll be looking for dx by dy because if we see that dy by dx would be 1 upon something. That is not a good type of condition. We would like to work on the numerator only. So we'll take dx by dy. Dx by dy is x cubed y cubed plus 2xy. Now if we take the term, involve the term 2xy on the left hand side, we get minus 2y times x is equal to y cube times x cube. So we can see that this is of the form Bernoulli's equation. Now what is a Bernoulli's equation? A general Bernoulli's equation is of the form x dash, or let's write it as dx by dt plus some function p of x, sorry, p of t, it should be p of t times x is equal to some function q of t times x to the power n. So here we can see that our pt is, if we replace y by t, this is basically minus 2t, and qt is equal to t cube. So we are in the framework of Bernoulli's equation. So standard way to solve Bernoulli's equation is to start again with a substitution, and we substitute as follows. We take some variable t to be equal to x to the power 1 minus n. This n here, the n is 3. So we take t to be 1 by x square. This gives us that x is equal to t to the power minus 2, and dt by dx is equal to minus 2 by x cube sorry, dt by dy. dt by dy is equal to minus 2 by x cube dx by dy. Why we differentiated with respect to y? Because we already had the term dx by dy in our problem. So this gives us that dx by dy is equal to minus x cube by 2 dt by dy. Now what was x in terms of t? Mainly we are trying to convert our problem. We want to convert our problem in terms of t and y so that we get rid of x. So what was x? X is t to the power minus 1 by 2. This gives us minus t to the power minus 3 by 2 by 2 dt by dy. Now putting this value of dx by dy, let's number it. 1, 2, using 2 and 1, we get minus t to the power 3 by 2 by 2 dt by dy plus minus 2y times x, which is t to the power minus 3 by 2, sorry, minus 1 by 2. And here we have minus 3 by 2 is equal to y cube x to the power 3. That means t to the power minus 3 by 2. Now multiplying equation 3 by minus 2 t to the power 3 by 2, we get dt by dy plus 4yt, because 3 by 2 minus 1 by 2 is 1, is equal to y cube minus 2y cube. Now this is of the form linear differential equation. We all know that the standard way to solve such an equation is to start with finding an integrating factor, and using that integrating factor we can directly reduce the solution. So what is the integrating factor for this equation 4? The integrating factor for equation 4 is given by e to the power integral of this function 4y dy, which is e to the power 2y square. Now using this integrating factor, the solution of equation 4 is given by t times integrating factor is equal to integral this non-linearity minus 2y cube times integrating factor dy plus some constant c. Now we'll solve this integral. It can be written as minus 2y square e to the power 2y square times y dy. plus c. Now if we take the substitution, u equals to 2y square, we get du is equal to 4y dy. So in order to get this 4y, I'll just multiply and divide it by 4. This is equal to minus 1 by 4 integration u e to the power u du plus some constant c. Now we'll solve this integral by using integration by parts, which is minus 1 by 4 u as it is, integral of e to the power u is eu, minus integral of derivative of the first function 1, integral of the second function e to the power u, and we know that the integral of e to the power u is again e to the power u. So we can replace this by e power u plus c. Taking e to the power u to be common, we get 1 minus u by 4 plus c. Replacing the value of u, what was u? U was 2y square. So this is e to the power 2y square, 1 minus 2y square by 4 plus some constant c. Therefore, our solution is t e to the power 2y square is equal to e to the power 2y square, 1 minus 2y square by 4 plus c. Now multiplying both sides by e to the power minus 2y square, we get t is equal to 1 minus 2y square by 4 plus c times e to the power minus 2y square. Now what was t? T was what substitution we had taken? T is 1 by x square. So replacing the value of t in the final solution, we get 1 by x square is equal to 1 minus 2y square by 4 plus some constant c times e to the power minus 2y square. So this gives us the solution. I hope the solution was fine. You were able to go through the steps. If you had any doubt in any step, please let me know. So the main important thing in this solution was this substitution. It was important to identify that the problem is something of the Bernoulli's type, and thus we use this substitution. Rest of the things were already rest of the things were what you had already done in your school time. So okay, then let's move to the next question. Next we'll see a question of linear differential equation, which you must have solved in your earlier classes. Just to recall it, solve 4x square y minus 6 dx plus x cube dy is equal to 0. Solution. We'll see how this problem can be rewritten. Let's see what is dy by dx. So d, or let's start with the basic. We can write x cube dy is equal to 6 minus 4x square by dx. This gives us that dy by dx is equal to 6 minus 4x square y by x cube, which is 6 by x cube plus 4 by x y. Now we can see that the maximum power of y over here is 1. So we are in the form of linear differential equation. Or we can write it dy by dx plus minus 4 by xy is equal to 6x cube. This is the most general linear differential equation. So we know how to solve such a differential equation. We start with finding the integrating factor. The integrating factor for 1 is given by e to the power integration of this function minus 4 by x dx, which is e to the power minus 4 ln x, which is 1 by x power 4. Oh my god, I did a mistake. So this is minus, this is plus. So we get a plus plus x power 4. Using this integrating factor, we can easily find the solution, which is given by, therefore, the solution is given as follows. Y times the integrating factor is equal to integration of this non-linearity x by 6 by x cubed times the integrating factor x power 4 dx plus some constant c. This gets cancelled out and we are left with x. So we get 6x squared by 2 plus c, which is basically 3x squared plus c. Therefore, we have y(x bar 4) is equal to 3x squared plus some constant c. This is our general solution. Till now, you had been looking for the integrating factor for a most general problem, most specific kind of problem. Sorry. So in such kind of problems, we know that the integrating factor is given by this. But there are several other problems which may not be linear. Still, there also we find integrating factor. So integrating factor is basically a function which after being multiplied by the equation makes the problem more easier to be solved. Moreover, it makes the problem to be exact. The equation turns out to be exact after multiplying the given equation by this integrating factor. It need not be exponential function. It can be some function of some other type also. We'll see that in next question. The next question is question 9. It asks you to find an integrating factor of the form x power h x power h times y power k, and then solve the problem given by 3y dx minus 2x dy plus x square y power minus 1 10y dx minus 6x dy equals to 0. So we'll find a function of the form x to the power h y to the power k, basically x some power of x times some power of y, so that if we multiply that function with equation 1, it turns out to be an exact equation. So firstly, let's Simplify the equation 1. We get, just clubbing the terms, multiplied by dx, we get 3y plus 10x square dx plus minus 2x minus 6x cubed by y dy is equal to 0. If we write this as some function mxy and this as some function nxy, we have del m by del y is equal to 3 and del n by del x is equal to minus 2 minus 18x squared by y. So since del m by del y is not equal to del n by del x, and equation 2 is not exact. Let h and k be such that if we multiply the equation second by x to the power h and y to the power k, then third equation 3 is exact. That means if we take this to be some function m bar xy, this to be some function n bar xy, we must get del m by del y is equal to del n bar by del x. That means this implies if m bar is equal to 3x power h y power k plus 1 plus 10x power h plus 2 y power k, and n bar is equal to minus 2x power h plus 1 y power k plus minus 6x power h plus 3 y power k minus 1. Then derivative of m with respect to y, which is equal to 3k plus 1 k plus 1 x power h y power k plus 10k x power h plus 2 y power k minus 1 is equal to m n bar x, the partial derivative of n bar with respect to x, which is minus 2 h plus 1 x power h y power k minus 6 h plus 3 x power h plus 2 y power k minus 1. We can see that the variables are same both the sides. All we need is that the coefficients of x bar h y bar k and x bar h plus 2 y bar k minus 1 should be equal. That is 3k plus 1 should be equal to minus 2 h plus 1 and 10k 10k should be equal to minus 6 h plus 3. This gives us 3k plus 2h should be equal to minus 5, and this gives us 10k plus 6h should be equal to minus 18, which is 5k plus 3h should be equal to minus 9. So we need to find h and k so that they satisfy these two equations. We'll be using the method of elimination to solve these two equations. So multiplying this equation by 5 and this one by 3, we get 15k plus 10h is equal to minus 25, and 15k plus 9h is equal to minus 27. Minus minus minus. These gets cancelled out. We are left with h equal to 2. Therefore, we have h is equal to 2, and which implies putting the value of h in either of these equations, we get k is equal to minus 5 plus 4 by minus 5 minus 4, sorry, minus 5 minus 4 by 3, which is minus 9 by 3 minus 3. Therefore, we get k equals to minus 3. Hence, x power 2 y power minus 3 is an integrating factor for equation, integrating factor for equation for our main equation, for equation 2. Because if you multiply equation 2 with the function x power 2 y power minus 3, our problem becomes equal to equation third, and which is exact. Hence, it acts as an integrating factor for equation second. Now, one can easily see that the solution of equation third is same as the solution of equation second. That is the beauty of integrating factor. Integrating factor is helping us to convert, to move to some other problem which is exact, and we know how to solve an exact equation. So that is why we are interested in finding an integrating factor, so that our problem becomes easier to solve. So now instead of solving equation second, we'll be solving equation 2 with specific values of h and k. So we have, therefore, now we have equation 3x square y power minus 2 plus 10x power 4 y power minus 3 dx plus minus 2x cube y minus 3 minus 6x power 4 y power minus 4 dy is equal to 0. One can easily see that this is an exact equation, and for an exact equation we know that the solution is given by fxy equals to c, where f is a function such that its derivative with respect to x is given by this function 3x square y power minus 2 plus 10x power 4 y power minus 3, and its derivative with respect to y is given by this function minus 2x cubed y power minus 3 minus 6x power 5 y power minus 4. Now, let's number these. What was the numbering? Second till third we were done. So we'll number it fourth and fifth. Now, if we integrate 4 with respect to x, we get function fxy integrating fourth by, sorry, with respect to x, we get fxy is equal to x cube by y square plus 2x power 5 by y cube plus some function of y. Why we took this gy? Because the derivative of gy with respect to x would turn out to be 0. So it would have happened that this, instead of a constant, we would have a function of y. Now this gives us the derivative of f with respect to y is equal to 2x cube by y cube minus 6x power 5 by y power 4 plus g dash y. We also know that from equation 5 that fy is equal to minus 2x cube by y cube minus 6x power 5 by y power 4. So these terms gets cancelled out. We are left with g dash y is equal to 0, which gives us that gy was actually a constant. Therefore, fxy is equal to x cube by y square plus 2x power 5 by y cube plus some constant c. And hence, our solution is given by x cube by y square plus 2x power 5 by y cube is equal to c. So in this question, we did two things. Firstly, we found an integrating factor, and then using that integrating factor, we solved an exact equation, and one can clearly see, if you want, you can check that this will be a solution of our main problem, which was not exact, but this would give the solution to our main problem as well. So let's move to the last question. This would also involve the integrating factor and exact equation. So our next question is, show that a constant A can be found so that x plus y to the power A is an integrating factor of 4x squared plus 2xy plus 6y dx plus 2x squared plus 9y plus 3x dy is equal to 0. And hence, solve, if you number it 1, solve equation 1. Using that integrating factor, we'll solve the corresponding exact equation and find the solution to problem 1. So, solution. Firstly, we have the equation 4x squared plus 2xy plus 6y dx plus 2x squared plus 9y plus 3x dy is equal to 0. Taking this taking this to be a function mxy and this to be a function nxy, we can see that partial derivative of m with respect to y is equal to 2x plus 6, and partial derivative of n with respect to x is 4x plus 3, which are not equal. Therefore, first is not exact. Now let's assume let a be such that x plus y to the power, after multiplying the equation with x plus y to the power a, 4x square plus 2xy plus 6y dx plus x plus y to the power a, 2x square plus 9y plus 3x dx is equal to 0 is exact. Now if we take this to be m bar and this to be n bar, we must have del m bar by del y is equal to del m bar by del x, which tells us that now del m bar by del y is equal to, we'll be using the product rule to differentiate m bar. We have x plus y to the power a as it is, differentiating the rest of the factor with respect to y. We have 2x plus 6 plus 4x square plus 2xy plus 6y as it is. We get a x plus y to the power a minus 1. Taking x plus y to the power a minus 1 common, we get x plus y times 2x plus 6 plus 4x square a plus 2xy a plus 6y a, which gives us x plus y to the power a minus 1, 4a plus 2 x square plus 6a plus 6y plus 6x plus 2 plus 2a xy. And similarly, we have del n by del y is equal to x plus y to the power a as it is, 4x plus 3 plus 2x square plus 9y plus 3x as it is, a times x plus y to the power a minus 1. A minus 1. Taking x plus y to the power a minus 1 common, we get x plus y, 4x plus 3 plus 2x square a plus 9y a plus 3x a, which is equal to x plus y to the power a minus 1 times 2a plus 4x square plus 9a plus 3y plus 3a plus 3x plus 4xy. Now we want del n bar by del y is should be equal to del m bar by del x. So let's number these equations. We had del equation 1. So mark it as 2 and this one is 3. From second and third, we see that all the coefficients of x square, y, x and xy must be sorry, must be equal. So in that case, we must have 4a plus 2 is equal to 2a plus 4, which gives us a should be equal to 1. Now let's see whether a equals to 1 is satisfying the rest of the coefficients as well. So 6a plus 6 is 12 and 9a plus 3 is again 12. So we are done with coefficient of y. Now let's see the coefficient of x. One side we have 6 and the other side we have 3a plus 3, which is again 6. We are done with coefficient of x. And the coefficient of y, xy. On one side we have 2 plus 2, which is equal to 4, and on the other side we have 4, so done. Therefore a equals to 1 will suffice our problem. Hence x plus y is an integrating factor for equation 1. Therefore, now we have an exact equation. Once we multiply the equation first with x plus y, we'll get an exact equation, and the solution of this exact equation will be the solution of our problem 1. So instead of solving the main problem, we'll be solving the exact equation. So let's solve this exact equation. We have what do we have? X plus y times 4x square plus 2xy plus 6y dx plus x plus y 2x square plus 9y plus 3x dy is equal to 0. One can clearly see that this is an exact equation. It would be good if you check it again. Sometimes it might happen that in the calculation we would have done some mistake and ended up with some different equation which might not be exact. So it is always good to check. So see that if we take this to be some function f1 and this to be some f2, del f1 by del y is equal to del f2 by del x. So we know that the solution of an exact equation is given by some function fxy equals to c. We know that the solution of this equation 4. The solution of 4 is given by fxy equals to c, where this function f is such that where derivative of f with respect to x is given by f1, which is x plus y times 4x square plus 2xy plus 6y, which is 4x cube plus 2xy, sorry, 2x square y plus 6xy plus 4x square y. Now this 4 plus 2x square y gives us 6x square y. So we'll replace it by 6x square y. Then we have 2xy square plus 6y square. And fy is given by f2, which is equal to x plus y times 2x square plus 9y plus 3x, which is 2x cube plus 9xy plus 3x square plus 2x square y plus 9y square plus 3xy. Now this 3xy and 9xy gives us 12xy. So let's replace it by 12xy. Let's number this equation as fifth and sixth. Now multiplying equation fifth with now integrating equation fifth with respect to x, we get integrating fifth with respect to x, we get fxy is equal to x power 4 plus 2x cube y plus 3x square y plus x square y square plus 6y square x plus some function g of y. This gives us that partial derivative of f with respect to y is equal to 6 2x cube plus 3x square plus 2x square y plus 12xy plus g dash y. Also, from equation 6, we already had fy, which was equal to 2x cube plus 12xy plus 3x square plus 2x square y plus 9y square. Now let's see, this terms gets cancelled out. 12xy, 12xy, 3x square, 3x square, 2x square by 2x square y. So we are left with g dash y is equal to 9y square, which gives us gy is equal to 3y cube. Putting this value of g here in the expression for function f, we get fxy is equal to x power 4 plus some constant c plus 2x cubed y plus 3x square y plus x square y square plus 6y square x plus 3y cube plus c. Therefore, the solution is given by fxy equals to some constant. Taking this constant on the other side and merging up all the constant as c, we get solution as x power 4 plus 2x cube y plus 3x square y plus x square y square plus 6y square x plus 3y cube is equal to some constant c. So this is the final solution. I hope you all were able to go through the steps that I had taken. I have tried to simplify the solution as much as I could. I had tried to explain each step as much as I could. So the main important thing in this solution was the integrating factor. Integrating factor is a very beautiful thing. It helps us to solve very difficult equation very easily. So yes, integrating factor is a great factor. So I hope you could get something through this lecture, and please let me know if you have any kind of doubt. You can very easily put a question on the NPTEL. Also you have some questioning area na? I'm not sure. So and in next class also you can ask. So from next class hopefully we'll be having recording live. Okay then, thank you.